The year was 2020. While the rest of the auto industry was racing towards smaller turbocharged engines, hybrids, and increasingly complicated technology, Ford did something that almost nobody expected. Deep inside its engineering centers, the company unveiled a massive, naturally aspirated pushrod V8 that looked like it had traveled through time. No overhead cams, no turbochargers, no gimmicks. Just 445 cubic inches of American iron, built to haul, tow, and survive punishment that would destroy many modern engines. Most people think the Ford 7.3-liter Godzilla exists because Ford wanted more horsepower. But what almost nobody knows is that horsepower was never the real mission. This engine was born because Ford had a problem, a serious one. Their aging 6.8-liter Triton V10 had reached the end of its life. Emissions regulations were tightening, commercial customers demanded better reliability, and diesel ownership was becoming increasingly expensive. Ford didn't just need another engine. They needed an entirely new philosophy. And what happened next may have created one of the greatest heavy-duty gasoline V8s ever built. To understand why the Godzilla matters, you have to go back nearly 2 decades. Throughout the early 2000s, Ford's Super Duty trucks relied heavily on 2 power plants. One was the modular Triton V10, the other was the legendary Power-Stroke diesel lineup. The V10 was dependable for many fleet operators, but it lacked low-end torque compared to modern competitors. It also had a reputation for spark plug issues that frustrated countless owners and mechanics. The diesels delivered incredible pulling power, but rising emissions equipment, diesel exhaust fluid systems, high-pressure fuel injection, particulate filters, and expensive maintenance scared away many commercial buyers. Construction companies, municipalities, RV owners, utility fleets, and farmers all wanted something simpler. They wanted gasoline reliability. They wanted diesel-like durability. And they wanted enough torque to pull thousands of pounds every single day without constantly worrying about the next repair bill or emissions system failure. Ford engineers understood exactly what customers were asking for. Instead of adapting an existing engine, they started with a blank sheet of paper. That decision changed everything. The engineering team asked themselves a simple question. If we could build the toughest gasoline truck engine possible today, knowing everything we've learned over the last 50 years, what would it look like? The answer surprised almost everyone. Instead of using the overhead cam modular architecture that Ford had invested in for decades, they returned to something many enthusiasts thought was obsolete, the pushrod V8. To some people, that sounded like moving backward. In reality, it was a giant leap forward. The pushrod layout offered significant advantages for heavy-duty trucks. It made the engine physically smaller despite its enormous displacement. It reduced overall height, making service easier. Fewer moving parts meant fewer potential failure points. The compact design also improved packaging under the hood, leaving more room for cooling systems, steering components, and maintenance access. For fleet managers responsible for hundreds of vehicles, easier maintenance access meant reduced labor costs and less downtime. That translated directly to money saved and productivity gained. But there was a problem. Ford couldn't simply copy old-school V8 technology. The engine still had to meet modern emissions standards, survive hundreds of thousands of miles, and produce competitive power without sacrificing efficiency. It needed to pass increasingly strict EPA certification. It had to deliver acceptable fuel economy numbers that wouldn't scare away buyers. And most importantly, it needed to prove itself more reliable than anything competitors were offering in the heavy-duty gasoline segment. That challenge became the heart of Project Godzilla. The specifications immediately revealed Ford's intentions. The engine displaced 445 cubic inches, or 7.3 liters, thanks to a massive 4.22-inch bore paired with a 3.98-inch stroke. That displacement figure wasn't arbitrary. Engineers calculated the exact size needed to deliver diesel-like torque curves without relying on forced induction. Compression ratio measured approximately 10.5:1, relatively conservative for a naturally aspirated gasoline engine, allowing it to operate safely under heavy loads using regular fuel in many applications. This meant customers wouldn't need to constantly feed it premium fuel, another cost savings that commercial operators immediately appreciated. In factory Super Duty trim, the Godzilla produced 430 horsepower at 5,500 revolutions per minute and an impressive 475 pound-feet of torque at roughly 4,000 revolutions per minute. Later calibrations increased output to around 430 horsepower and 485 pound-feet in some configurations, while crate engine versions offered similar ratings with tuning flexibility. Those numbers looked good on paper, but they didn't tell the real story. Peak horsepower sells trucks. Torque across the entire RPM range keeps businesses running. Ford intentionally designed the engine to produce broad, usable torque instead of chasing high RPM horsepower figures that would never be used in real-world towing situations. The camshaft profile, intake runners, combustion chamber design, and valve timing all work together to create immediate pulling power from barely off idle all the way through the mid-range. This wasn't an engine built for dyno competitions. It was built for impossible workdays, and then the real testing began. Ford engineers subjected prototypes to brutal durability cycles. Engines spent thousands of hours at sustained loads that simulated towing maximum weight trailers across mountains in scorching summer temperatures. Others endured repeated cold starts in freezing environments, where oil becomes thick and internal clearances shrink, creating some of the harshest wear conditions an engine ever faces. Some engines ran continuously until internal components finally failed, not because Ford expected customers to experience those conditions, but because they wanted to know exactly where every weakness existed. Most people never see this side of engine development. A prototype might spend weeks running wide open on a dynamometer without ever leaving the test cell. Sensors monitor oil pressure, bearing temperatures, coolant flow, piston expansion, crankshaft vibration, and combustion stability every second. If something breaks, engineers don't just replace the part, they ask why. They analyze the metallurgy, they examine wear patterns under microscopes, they run computer simulations to understand stress distribution, they modify the design and test again. This process repeats hundreds of times before a single engine ever reaches a customer. It's expensive, time-consuming, and absolutely essential for creating an engine that will survive decades of commercial abuse. One of the biggest priorities involved lubrication. Heavy-duty trucks often spend hours climbing grades while towing enormous loads. Oil control becomes absolutely critical during those conditions. The Godzilla uses a variable displacement oil pump along with carefully engineered oil passages feeding the crankshaft, camshaft, piston cooling, and valve train. Engineers focused on maintaining stable oil pressure even under sustained high-temperature operation when conventional systems might struggle. The oil pump adjusts its output based on engine speed and load, reducing parasitic drag when maximum flow isn't needed while ensuring adequate pressure during extreme conditions. Cooling received equal attention. The cast-iron deep skirt block provides tremendous rigidity while supporting 6-bolt main bearing caps, increasing bottom-end strength under continuous heavy loads. Cast iron may seem old-fashioned, but it offers superior durability and heat resistance compared to aluminum in extreme-duty applications. Aluminum cylinder heads help reduce weight while improving heat transfer. Large coolant passages ensure even temperature distribution throughout the block, minimizing localized hotspots that could eventually cause cracking or head gasket issues. The cooling system capacity was sized generously, understanding that this engine would spend much of its life working hard rather than cruising empty on highways. Simple didn't mean primitive. It meant optimized. The forged steel crankshaft became another cornerstone of the design. Combined with durable connecting rods and stout pistons, the rotating assembly was engineered for commercial longevity rather than flashy peak numbers. Although production engines use powdered metal connecting rods instead of fully forged racing components, the bottom end proved remarkably strong. Ford's powdered metal technology had evolved significantly over decades, producing components that rivaled forged pieces in many applications while offering better dimensional consistency and lower manufacturing costs. How strong? Aftermarket builders quickly found the answer. Within months of release, performance shops began installing superchargers and turbocharger systems. Stock long-block Godzilla engines started producing 700 horsepower, then 900, then over 1,000 horsepower. Some highly modified builds eventually crossed the 500 horsepower mark with upgraded internals and forced induction. That shocked nearly everyone, because underneath its work truck appearance was an engine with enormous hidden potential. But there was another surprise waiting. Ford had quietly designed the engine with performance enthusiasts in mind. Unlike many modern truck engines buried beneath layers of electronics and packaging nightmares, the Godzilla remained remarkably accessible. The pushrod valvetrain's simplified camshaft swaps, the compact dimensions allowed easy installation into older Mustangs, F-Series trucks, Broncos, Fox body cars, and custom builds. The relatively simple electronics meant tuning didn't require defeating dozens of safety systems and complicated subsystems. Soon, the aftermarket exploded. Performance camshafts, high-flow intake manifolds, cylinder head upgrades, standalone engine management systems, turbo kits, supercharger packages, custom exhaust headers, billet oil pans, upgraded valve springs, high-flow fuel systems. Within only a few years, the Godzilla had become one of the hottest swap engines in America. Online forums dedicated to the platform grew exponentially. Facebook groups filled with build threads and troubleshooting advice. YouTube channels documented complete engine swaps step by step. The community that developed around this engine became one of the most active and supportive in the automotive world. You can probably guess what happened next. Racing teams noticed. Drag racers discovered that the massive displacement delivered incredible launches off the starting line. The torque curve meant less need for complex transmissions and torque converters. Truck pull competitors appreciated the engine's brutal low-end torque that could lug down and keep pulling when other engines would fall off their power curve. Off-road builders loved its compact dimensions and robust construction that could survive the violent impacts and sustained high RPM abuse of desert racing. At events across the country, modified Godzilla-powered vehicles started posting quarter-mile times deep into the 9-second range, with some dedicated drag builds pushing well into the 8-second zone after extensive modifications. Top speeds mattered less than raw acceleration, and the engine delivered it in spectacular fashion. The sound of a modified Godzilla at wide-open throttle became unmistakable, a deep, rumbling roar that announced serious horsepower. Yet despite all that performance, Ford never lost sight of the original mission. Commercial durability remained the priority. Fleet operators began reporting impressive reliability in severe service. Tow vehicles accumulated hundreds of thousands of miles hauling equipment. Motorhome owners praised the engine's predictable power delivery across mountain passes, noting how it maintained speed on grades where smaller engines struggled. Utility companies appreciated lower operating costs compared with diesel alternatives. Small business owners who couldn't afford unexpected downtime found the Godzilla delivered the dependability they desperately needed. Fuel economy wasn't revolutionary. Nobody buying a 7.3-liter gasoline V8 expected hybrid efficiency. Real-world numbers typically ranged from around 10 to 14 miles per gallon depending on load, driving conditions, and application. That wasn't great, but it wasn't terrible either for an engine of this size doing serious work. But maintenance costs often proved dramatically lower than modern diesel engines equipped with complex emissions hardware. Eliminating turbochargers, high-pressure diesel injection systems, diesel particulate filters, selective catalytic reduction systems, and DEF components simplified ownership considerably. Oil changes used conventional or synthetic oil without expensive diesel-specific formulations. Spark plugs, while numbering 16 total, were accessible and inexpensive. Fuel filters cost a fraction of diesel equivalents. That simplicity became one of the Godzilla's greatest strengths. Sometimes the best engineering solution isn't adding more technology, it's removing unnecessary complexity. Ford's engineers understood that perfectly. The timing system reflected the same philosophy. Instead of multiple long timing chains stretching across dual overhead camshafts, the pushrod design required a much simpler arrangement. Fewer components meant lower friction, reduced maintenance concerns, and improved long-term durability. When timing components eventually needed replacement hundreds of thousands of miles down the road, the job was straightforward rather than requiring complete engine disassembly. Even the valve train embraced practicality. 2 valves per cylinder may sound outdated compared with 4-valve overhead cam engines, but larger valves, optimized combustion chambers, and careful airflow development produced excellent breathing characteristics within the engine's intended operating range. Ford's engineers spent countless hours in computational fluid dynamics simulations and flow bench testing to maximize efficiency. The result was an engine that breathed well enough to make serious power without the complexity and maintenance requirements of multi-valve overhead cam designs. For heavy-duty work, high RPM airflow wasn't the goal. Instant torque was, and the Godzilla delivered exactly that. Of course, no engine is perfect. Early owners reported occasional issues, including isolated lifter concerns and some spark plug wire failures due to heat exposure in demanding applications. Certain engines also experienced minor oil consumption variations. However, compared to the widespread catastrophic failures that have plagued some modern engine families, these problems remained relatively limited, and Ford addressed many concerns through updated parts and service procedures. The company issued technical service bulletins, revised component designs where necessary, and worked with dealers to ensure problems were resolved quickly. The core architecture itself proved exceptionally durable. That's why so many performance builders continue using factory blocks for astonishing horsepower levels. Few production truck engines earn that kind of respect. But perhaps the most remarkable part of the Godzilla story isn't found on a dyno sheet. It's what this engine represents. For decades, manufacturers convinced buyers that progress always meant smaller displacement, greater complexity, more electronics, and more forced induction. Engineers became obsessed with chasing efficiency numbers and emissions targets by adding layer after layer of technology. Engines became difficult to service, expensive to repair, and sometimes less reliable despite all the advanced engineering. Then Ford introduced an enormous, naturally aspirated pushrod V8. Instead of chasing every trend, they focused on solving real customer problems: reliable towing, predictable maintenance, accessible repairs, long service life, affordable ownership. The result wasn't just another engine. It became a statement. Old-school engineering principles still had tremendous value when combined with modern materials, advanced manufacturing, computational design, and decades of accumulated experience. The Godzilla proved you could meet emission standards without impossible complexity. You could deliver excellent reliability without exotic materials. You could build an engine that worked hard every day without falling apart. That's why the Godzilla earned its name. Not because it was the biggest, not because it was the fastest, but because it was built to survive almost anything. Today, the 7.3-liter Godzilla continues powering Super Duty trucks, commercial chassis, motorhomes, and countless custom builds. Meanwhile, aftermarket companies continue pushing the platform into horsepower territory few imagined possible when Ford introduced it in 2020. New performance parts release monthly. Engine builders develop specialized combinations for specific applications. The platform continues evolving even as production engines maintain their focus on commercial durability. Its legacy is already becoming clear. It has revived enthusiasm for naturally aspirated American V8s. It has inspired one of the fastest-growing aftermarket communities in recent memory. And it has reminded an entire industry that simplicity, when executed brilliantly, can outperform complexity. Young enthusiasts who grew up with turbocharged 4 cylinders suddenly discovered the appeal of massive displacement and immediate throttle response. Experienced builders who remembered the golden age of American V8s found a modern platform worthy of their skills. In an era dominated by downsized turbocharged engines, the Godzilla stands as proof that there's still room for massive displacement, cast iron, push rods, and honest mechanical engineering. That's what makes this story so remarkable. Ford didn't just build another truck engine. They proved that sometimes the future isn't about abandoning the past, it's about perfecting it. The 7.3 Godzilla brought back old-school power, but it did it with modern precision, modern durability, and a level of engineering that may keep it relevant for decades to come. If you enjoyed this deep dive, let me know in the comments which legendary engine you'd like to see next. And make sure to subscribe, because there are still plenty of forgotten engines, racing legends, and engineering masterpieces waiting to have their real stories told.